Today we're going to work with the normal distribution. So we're going to do Chapter 10, A, B, and C, pretty much all of Chapter 10 all in one day. The normal distribution is when our data is shaped in a bell. So normal distribution means that we've got a lot of data kind of clustered around the middle, and then it's symmetric both directions with these little tails. There's not one direction where there's a lot more data than the other. It's very evenly distributed across. So no major outliers, nothing like that. So the normal distribution is the most important and most widely used distribution in statistics. The reason that is because it occurs very often. So normal distributed data is going to form a bell shape. So you may hear this as the bell curve. And it just has a lot of data close to the middle, and then it's symmetric on both ends. Not normally distributed data may have outliers, might be not symmetric, random, okay? So that data that's not normally distributed is not going to form this nice even bell shape. So if our data forms a normal curve or a bell curve, then we can do a lot of different things with it to estimate the chance of data falling in a certain place. So the normal distribution is symmetric about the mean, which is mu, that little guy there. It's like a U with an extra tail. So this value here, the center, is the mean, the mu. And you can see we have like the same amount of data on both sides. It's normally distributed. It's symmetric across this line. For the normal distribution, the mean, median, and mode are all the same value. So our mean is this number here. It's also the middle of our data. And it's the most occurring. If you think about this as a bar chart, this would be the highest bar. So all three of these values are the same whenever we're dealing with normally distributed data. The area under the normal curve is equal to our percentiles. And we'll talk about that here in a second. 4 says the normal distributions are denser in the middle and less dense on the edge. So denser in the middle and less dense on the edges. So we have more data clustered here in the middle with less data kind of starts spreading out on each side. An example of where the normal distribution would occur is ACT scores. So typically we have a large chunk of students who have an ACT score that's kind of in the middle. So average, middle, okay, middle ACT scores. And then we've got some students who have higher ACT scores, a couple, right? There's not a lot that are up here at the 36s, but as you get closer to 36, you get less and less and less. And then the same thing going down the other direction, okay? So ACT score is an example. Another example might be the heights of people. So if we think about men in the United States, okay, there's going to be a lot of people who are right around the average height. I don't know, for a male in the United States, it might be like 5'11" or something, 5'10". There's a lot of people that are right around that height. There's a lot of people that are right around it, not necessarily exactly that height, but right around that height. And then there's some people who are really tall, people who are really short, and then it kind of gets less and less and less and less as you go up. Okay, so heights is an example of something that might be normally distributed. 5 says the normal distributions are defined by two parameters: the mean, mu, and the standard deviation, that guy, the knocked over 6. So the mean and the standard deviation are the two values that determine what a normal distribution is going to look like. So the mean tells us where the center is located. So mean, it's the center of the bell curve. And the standard deviation tells us how spread out the data is. How much is it increasing from there? So here, this mu is the mean. That's the middle of our data. Mu, okay, that's the mean. This says mu plus our standard deviation. So it says mu plus our standard deviation here. This is sigma, so this would indicate one standard deviation above. So this is the mean plus one standard deviation. Okay? This is the mean plus two standard deviations. So once you're two standard deviations away, your data is getting pretty scarce. Okay? Less and less and less. These percentages are all approximate. On the actual IB exam, you will not have to use the approximate percentages for the normal distribution. They're just kind of good to know. So on 10A, they have you use the approximates, and then on 10B, they have you use your graphing calculator to get the exact. So let's look at how these approximates would work. So this 34.13% represents that between the mean and one standard deviation above the mean. So between the middle number and one standard deviation above, we have 34.13% of our data. So 34.13% of our data lies between the mean and one standard deviation above. Okay, right here. Okay, between one standard deviation less and two standard deviations less, between these two values, we have 13.59% of our data. And so we can figure out lots of things using these estimates. And then in 10B, we're going to look at how to do it more precisely with our graphing calculator. All right, so notation. It says we can use the following notation to describe a set of data that is normally distributed. This says our variable x is approximately normally distributed with a mean of whatever and a standard deviation squared of whatever. They put the standard deviation squared because that is, this is your standard deviation. And sigma squared is your variance. Okay, so it's just kind of a notation. So we would read this as x is a random variable that is approximately normally distributed with a mean of mu and a standard and a variance of sigma squared. All right, so how does this work with an actual problem? So it says the chest measurements of 18-year-old male footballers are normally distributed with a mean of 95, that seems important, and a standard deviation of 8. Represent this information on a normal curve. So I'm going to make a little normal curve at the bottom here. Normal curves are like a bell shape. Okay. We said up above our mean is kind of the peak of the bell. It's the middle. And in this case, it says the mean is 95. We have a standard deviation of 8 centimeters. So I'm going to try to put my lines similar to the way they are up here. So 1 standard deviation above, 2, 3 would be down there. 1, 2, 3 would be down there. So if I go 1 standard deviation above the mean, where 8 is our standard deviation, so we'd go from 95 plus 8, which is 103. So 1 standard deviation above the mean is 103 centimeters. If we go 2 standard deviations, we just add 8 again, which is 111. 3 standard deviations, we go to 119. So this is a standard deviation. It's 8 across. See if I can zoom in a little more. Still be clear. All right, that looks pretty good. We can also go the other direction. So we take our 8 away from the mean. So 95 minus 8 is 87. Minus 8 is 79. Minus 8 is 71. So let's see if we can answer the questions that they're asking us to. What percent of data is between 87 and 103? So 87 is here, 103 is there. So if we look at our estimating chart up above, this section has 34.13, so does that one. So right here, this has 34.13%, so does this one. So that means between 95 and 103, it's 34%, and between 87 and 95, it's 34%. So the percent between 87 and 103 would be those added together. .26%. This is approximately. So what percent of data is between 87 and 103 centimeters? About 68.26%. Okay, the second part says what percent of data is between 103 and 111. Okay, so 103 is here, 111 is there. If we look up above, that section is 13.59. And so that's what our answer is here. All right, what percent is greater than 111? Well, we have this section labeled as 2.15% from our graph above. And this little tail is labeled as 0.13%. So greater than 111 would be these two sections here. So we would add 2.15 plus 0.13, which gives us 2.28%. Okay, so we're picking out which percentages go with each section. Find the probability that the chest measurement of a randomly chosen football player is between 87 and 111. So we already have all those percents labeled. So starting at 87, this section's 34.13. This section's 34.13. We're going all the way to 111, so we've got also a 13.59. So that's 81.85% of football players that have a chest measurement between 87 and 111. As a probability, this would be fine, but a better answer would be 0.8185. Probabilities out of 1 typically, but you could also leave it as a percent. All right, find the value of K such that that approximately 16% of chest measurements are below K. Okay, so we need to, I'm going to put these down. All right, so those are all of our percentages. So if you have a chest measurement of 71, then that means that 0.13% is less than. But we need approximately 16% of the people below that value. So at 71, there's only 0.13. At 79, it'd be the 0.13 and also the 2.15. So at 79, 2.28% are less than that. If I go to the next one, I add the 13.59. Okay, so at 87, there's 15.87 less than, and that's pretty close to 16. So we would say approximately 87 centimeters. So at 87 centimeters, approximately 16% of chest measurements are less than that. So this, and that. All right, so let's look at the back. On the back, we're going to start, instead of using the approximates, we're going to start using the graphing calculator to help us out. So we have some notation for this. This notation represents the probability that a data value is less than a certain number. So the probability that a random variable is less than or equal to whatever that number is. This notation is the probability that a random variable is between two different numbers. So Okay, so one thing we've got is like, okay, so we got this 180, or we got 87 here. What percent's less than? So, okay, we'd add all those up. The other thing we have is what percent's between. So, like between 87 and 95, okay? And so we'd look at the between. So those are the two notations for those, either less than or between. And we're going to have different buttons we can push to find these. So, calculator instructions. It says, normal CDF finds the area under the normal curve between two bounds given the mean and standard deviation. Okay? Finds the area under a normal curve between two bounds. So, for instance, the percent of data between 87 and 95. Okay? We could find that. Inverse normal, INV norm, finds the data value x for which the area under the curve is less than some given area. Also need mean and standard deviation. So this is more like the last question here. Okay? It finds the k value where there's a certain percent that's less than that. All right, so let's see if we can answer these questions. So this says x is approximately normal distributed with a mean of 10 and a standard deviation, sigma, it says 2.3 squared, so our standard deviation is 2.3. So we want to find the probability that our value is between 8 and 11. So we're going to go calculator. You have to have a graphing calculator. Practice pushing these buttons on your calculator. So we're going to go second vars, and that's where this normal CDF and also inverse normal appears. So we're going to use normal CDF today. Okay, what do each of these mean? So lower and upper are lower and upper bounds. So if I look here, 8 is the lower bound for my data, 11 is the upper. So this calculator can find the data, the percent of data between these two numbers for this normal distribution. So our lower is 8, our upper is 11. This says mean, mu, 10, standard deviation 2.3. Paste, enter, and it'll give us the percentage. So this says 0.4758, so you could write it as a percent or as a decimal. It says probabilities, so we'll write it as a decimal instead, 473 sig fig, so 6. That means about 47.6% of data is between 8 and 11. Kind of makes sense that there should be quite a bit of data since 10 is our mean. Okay. The next one says x is less than 12. So we're going to go to the same place, second distribution, normal CDF. Now, less than 12. So when I think about what my lower bound is, 12 is my upper bound because we want everything less than 12. So 12 is the highest. Our lower bound is needs to be a very small number. So I'm going to put negative and then just type a bunch of 9s. It doesn't matter really how many 9s. I think I probably clicked that 10 times. I don't know. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Oh, I clicked it 13 times. Okay? But it needs to be a very small negative number because there is no lower bound. Okay? So we give it a very small negative number. Same mean, same standard deviation. We paste it, and that says that 80%, or we have a probability of 0.808, so a little over 80% of our data is less than 12. For this one, x is greater than 9, same thing. Second distribution, normal CDF. Now we want x to be bigger than 9, so 9 is the lowest we want it to be. Bigger than 9, so I'm going to put a really big number here, put a bunch of 9s. Same mean, same standard deviation, and this tells me that 66.8% of my data is greater than 9. Oops, I've been writing like this. Okay. So 0.668 is the probability our data is greater than 9. When it says illustrate the results, okay, so we have a normal curve. Our mean is 10. Our standard deviation is 2.3, so that'd be 12.3, 14.6, 16.9, right? Adding 2.3, we'd take away 2.3, going the other direction, so 7.7, 5.4, 3.1, okay? And so between 8 and 11 would fall like here, between 7.7 and 10, and 11 would be like here. Alright, so that would be the first one. Okay, that was 47% or so of our data. Less than 12, 12 would be, okay, there's 12.3, so 12 would be like here. Less than 12, it makes sense that that should be more than half of our data, since that's bigger than our mean. Less than 12 is all this stuff, okay? So that was 80% approximately. And then the greater than 9, let's see, 9 would be just smaller than 10, was 66%, okay? Which 9 is a little bit less than the mean, so it should be more than half, okay? It's greater than. Oh, I should have drawn that all down here. I thought I made another question there, but that is the same question. So you could do a bunch of work right here. Okay, that's all one example. All right, last question. It says in 1972, the heights of rugby players were approximately normal distributed, with a mean of 179 centimeters and a standard deviation of 7. Find the probability that a randomly selected player in 1972 was at least 75 centimeters tall. So that means that they need to be greater than or equal to 175 centimeters. Okay, so if you're going to be at least a certain height, you have to be that height or taller. So I'm going to do second distribution, normal CDF. We're doing greater than 175, so the lowest would be 175. Anything bigger, so all the way to a really large number. And let's see, my mean was 179, standard deviation was 7. And that should spit out, find the probability. So we'll write it as a decimal. There it is. Okay. To do between two numbers, I think this one's a little easier to see. We do normal CDF. The lowest is 170. The highest is 190. Same mean, same standard deviation. And so this tells us that about 84% are between those two heights. And for these, we have to find the k value such that x is less than or equal to k. And it needs to give us 16%. So we did a 16% on the front.
Sorry, I can't.
So this is going to be our other button. So this is second distribution, inverse normal, and some different options are going to pop up. For area, it needs to be the area less than. So in this case, we have this, we have our mean. At some point, we've reached 16% of our data. And we want to know for what value does that happen at. So our mean here was 179. Okay, we've got a standard deviation, but at what value are 16% of people shorter than that? So in this case, our area is 0.16. That represents this 16%. Our mean is the 179, and our standard deviation is 7. So this tells me 172. So out of 172, 16% of data is smaller than that. So for this one, we used second distribution. We used the inverse normal. and our area was 0.16, mean 179, standard deviation 7. This one says, for what value of x is x greater than k? So is x bigger than? Gives us an area of 40%. So we're looking at this. Because it's greater than, here's our mean, that would be 50% of data is bigger than the mean in this case. So at some value, 40% is bigger than it. Your calculator, you have to tell it the less than. So if there's 40% here, there's 60% over there. And so whenever I type this one in, second vars, inverse normal, 0.6. We do not use the 0.4, and that's because it told us the area greater than, so we need to, our calculator needs us to tell it the area less than. Same mean, same standard deviation, and there it is, 180.77. So at 180.77 centimeters, 40% of people are taller than that. So that one we pressed second distribution, inverse normal, and for our area we use 0.6 because that's the area less than. Our mean is 179 and our standard deviation was 7. Okay. Alright, this should help you get started on 10A, B, and C. C, you're probably going to need a little more help with, and so I will be helping you guys a little more with C kind of as we go through it, but this gets you started.